So in this session, we'll be doing now section 2.4, rational expressions. Okay, so in this particular lecture, factoring will be helpful. We will do a lot of factoring within this lecture here. In fact, from here onwards, your factoring will be helpful. So I hope you will um, practice on factoring expressions, okay? Because yeah, the methods there are really needed, okay? From this lecture onwards. So what are these rational expressions? A rational expression, it's just a quotient of two polynomials. Okay? For example, the following here are rational expressions. You have x cubed plus x plus 1 over x. So x cubed plus x plus 1, this is a polynomial. Over x, that's the x is a polynomial. So this is a rational expression. Similarly here, x squared plus 1 over x to the 5 plus 1, or this expression here, x over x cubed minus 1. So these are rational expressions. Also, this guy here, x to the 4 minus x squared plus 1 over 4. This is a rational expression because, well, you have a polynomial in the numerator. You also have a polynomial on the denominator. The polynomial on the denominator, it's the constant polynomial. It has degree 0. So it's still a polynomial. But what's good thing in showing this example is that this can be translated into, or can be rewritten as 1/4 x to the 4 minus 1/4 x squared plus 1/4. And this is a polynomial with coefficients 1/4, 0, negative 1/4, 0, positive 1/4. So the point of this example here is that all polynomials, they are also rationals. Okay? All polynomials are also rationals. You can just put denominator 1, and 1 is a polynomial. So it's a rational expression. Okay? And also, if we have two variables, we have x squared y over x minus y squared. Okay? So this expression here, this is still a rational expression, but involves two variables. Okay? You have the variables x and y. Now, suppose we have a rational expression in one variable. Okay? And we have the polynomial p of x over the polynomial q of x. Okay? The polynomial p of x, we call it the numerator as usual. The same as the rational numbers or your fractions. And the polynomial q of x, we call that denominator. Okay? If the polynomial p of x and q of x do not contain common factors, except, again, 1 and negative 1, we say that the rational expression is reduced to lowest terms or is simplified. Okay? And the goal, if you have rational expressions, the usual goal is to simplify the rational expression. Okay? The same definitions are used if P or Q are polynomials in two variables or three variables or more. Okay, but for now, we'll be looking at expressions um, with only one variable, x. But we are not restricted to that. We'll see several examples or we'll see several exercises where you have more than one variable. Okay? When dealing with rational expressions, one assumes that the denominator does not take the value 0. Of course, we don't divide by 0. Okay? So, if you have a rational expression on you have a rational expression of this form, the denominator is q of x, you will have to check the value for x for which q of x will be 0. Okay? So you have a value, you evaluate that value into q of x or into your denominator. After evaluating, you have 0. Okay? You will remove that value x in the conversation. Okay? Because we don't want division by 0. Okay? So one assumes that the denominator does not take the value 0. So more precisely, if you have this rational expression in the variable x, one only considers x for which q of x is not equal to 0. Later, um, later, the collection of all x's for which this guy here holds, okay, we call it the domain of the rational expression. So we will define this domain again later in the course. Okay? But from now onwards, you will hear me or you might hear me saying the term domain. It only means that the domain, it's the collection of all x's for which the expression is valid, in the sense that the expression becomes a real number after evaluating. So it's in here. We call the set the domain. Okay? Our goal, as I have said earlier, is to simplify rational expressions. And in order to do this, one needs the skill of factoring. What you do, you have a polynomial in the numerator, you have a polynomial on the denominator. What we do is to factor each polynomial and then check the common factors. And then you remove them. Okay? And then you remove them. And then you will get the simplified form. Okay? So in the set of real numbers, we have the cancellation property. Okay? You have AC over BC, provided that B and C are not equal to 0 because you have a denominator, BC. Okay? You can cancel the C. This C here and then this C here, you can cancel that. That's why it's called cancellation law. So AC over BC, that's equal to A over B. Okay? So we also have cancellation law in the polynomials. Okay? Or in the rational expression. So to simplify rational expressions, one cancels out factors common to both numerator and denominator. And of course, excluding 1 and -1. Okay? So for example, we want to simplify x squared plus 6x plus 9 over 12 plus x minus x squared. So when you are given a rational expression, your first goal is to factor the polynomial expressions. And these two guys here are factorable. So if we factor each of them, so from here, x squared plus 6x plus 9, it can be factored into x plus 3 squared. And then in the denominator, 12 plus x minus x squared, you can factor this into this expression here, 4 minus x times 3 plus x. Okay? And now, as you can see, you have x plus 3 in the numerator, you have 3 plus x on the denominator. But remember, a plus b, this is also equal to b plus a. So this 3 plus x here, it's the same as x plus 3, which means that x plus 3 is a common factor. And therefore, if we just write x plus 3 as x plus 3 squared as x plus 3 times x plus 3, we clearly see x plus 3 here and here, they will cancel each other. So you will end up with this expression. So for this, we cancel this, and we will have x plus 3 over 4 minus x. So this is our final expression. Okay? Any questions? So, like I said, factoring will be crucial. So you have to practice on your factoring. Okay? Next example here, we have x squared minus 1 over x cubed minus 1. Numerator here, difference of two squares. Denominator, difference of two cubes. Both of them are factorable. So in here, we have x squared minus 1 over x cubed minus 1. They can be factored into the following. So x squared minus 1, that's x plus 1, x minus 1. On the other hand, x cubed minus 1, you can factor that as x minus 1 times x squared plus x plus 1. And then you see x minus 1 is a common factor. You just cancel them. You'll end up with x plus 1 over x squared plus x plus 1. Okay? Now let us look at the next example. So we have x cubed plus x over x to the 4 minus 1. So here we have x cubed plus x over x to the 4 minus 1. And you can, x cubed plus x over x to the 4 minus 1. So you can factor x cubed plus x in here. X is a common factor. In here, you have x to the 4 minus 1. You can factor this because you can treat x to the 4 as x squared squared. Okay? So this guy here, this is just x squared quantity squared. So this is difference of two squares. Okay? So for the numerator, you have x times x squared plus 1. For the denominator, you have x squared minus 1 times x squared plus 1. And then you will see that x squared plus 1 is a common factor. And in here, x squared minus 1, it's still factorable because it's a difference of two squares. So you factor it as x minus 1 times x plus 1. So you cancel now x squared plus 1 times x squared plus 1 there. Sorry, x squared plus 1 over x squared plus 1 there. And then you will end up with this final answer. By the way, when you are writing the simplified version of a rational expression, so listen very carefully, you have to retain the final answer, the expressions in factored form. Okay? You do not multiply this. Just keep it that way. Okay? You keep everything in factored form. Why? Because when they are written in factored form, you can easily see whether there are still common factors. Okay? There are students who after factoring they will multiply them again, and then at the end they were not able to simplify the expression because when they multiplied, you won't see easily the common factor if there are any. So always write the final expressions in factored form. Okay? So questions in simplifying rational expressions. Now, we will also work on operations, or we will also study operations on rational expressions. So we start with multiplication and division of rational expressions. So we recall this, okay? If you have real numbers, if you have fractions, a over b and c over d, if you multiply them, all you need to do is to multiply the numerator and then divided by multiply the denominator. So you have AC over BD. Of course, we are assuming here that B is not equal to 0 and D is not equal to 0. Otherwise, we have zero division, which is not defined. And if we are dividing expressions, rational expressions to be more precise, you have here A over B all over C over D. Okay? This is the same as A over B times D over C. So if you look at this and this guy here, okay, this is the reciprocal of this. So from division, okay, from division of rational expressions, you can convert it to multiplication, but be sure that the big denominator, I usually call this guy here the big denominator, okay? The big denominator, you have to make sure to get the reciprocal before multiplying. So from C over D here, it becomes D over C when you multiply. Okay? And we know the product of fractions, so we apply this. So this becomes AD over BC. And from here, as you can see, you cannot have B equals 0 because B is a denominator here. You cannot also have D equals 0 because D is a denominator here. Furthermore, you cannot have C equals 0 because if C equals 0, then this whole thing here will be 0. But this is also a denominator of a larger rational expression. Okay? So we have these conditions. B not equal to 0, C not equal to 0, D not equal to 0. So we also do the same thing for rational expressions. We use the same definition. So a note here, it is helpful to write each expression in factored form so that common factors can be cancelled or can be detected easily and therefore be cancelled. Okay? Always leave the final answer in factored form. Okay? And then when you do this, okay, when you multiply rational expressions, you multiply or you divide rational expressions, you will still need to simplify it, which means canceling common factors. Okay? For example, we want to perform the indicated operations and then we simplify. So look at this, leave the final answer in factored form. We have 3x plus 6 over 5x squared. We multiply it to x over x squared minus 4. So if we do this, okay, this is this guy here, 3x plus 6, you can factor 3. 3 is a common factor here. So you have 3 times x plus 2. For the denominator, you can actually leave this as 5x squared. But if you factor x squared into x times x, okay, you will see immediately that there is a common factor. If you now consider this right factor here, of course, x is still x, and therefore, x is a common factor there. You have x here in the denominator, x also in the numerator. And x squared minus 4, you can factor that into x minus 2 times x plus 2. So, we can now multiply them. You put them into a single numerator. You also put them into a single denominator. Okay? And then you see x plus 2 here and x plus 2 here. They will be cancelled. So this and this. And then you also see the x in the numerator and x in the denominator. So this guy here will cancel this guy here. And therefore, you'll be left with this expression. So again, it's written in factored form. And we easily see that there are no more common factors. So this is the final expression. Any questions? Okay. Suppose we have the division. So 6x over x squared minus 4 all over 3x minus 9 over 2x plus 4. Okay? So we have this division. Now, all the time, if I'm going to use this notation for our division, okay, you will see I will be using a longer line. Okay, a longer line if I am dividing rational expression by rational expression. So the longer line tells you what is your numerator and what is your denominator. And again, I call them the big numerator and big denominator. So in here, this is my big numerator, and then this is your big denominator. And then, if, like for this example, I am dividing rational expression by rational expression, I have those small numerator and small denominator. So for the big numerator, this is the small numerator and this is the small denominator. And then for the big denominator, this is your small numerator, this is your small denominator. So it's just for me, okay? It's not a standard term, big and small numerator, denominator, but yeah, okay? So what I'm saying is you will clearly see what the big numerator is and what the small numerator is if you will see this type of notation in the exam. Okay? But of course, instead of using this long line as my division symbol, okay, I will be also using this symbol. Okay? So instead of writing this division this way, I could have written that in this way. 6x over x squared minus 4 divided by 3x minus 9 over 2x plus 4. So I could have written this one here this way. So either this way or this way, I mean division. Okay? So now we have division in here. Okay? We convert this to multiplication. But notice this guy here, okay, the big denominator, when we converted it to multiplication, I have the reciprocal. So the big denominator, it's 3x minus 9 over 2x plus 4. The whole expression here converted to multiplication, I now have this factor, 2x plus 4 over 3x minus 9. So reciprocal. We have to look for the reciprocal, or we have to get the reciprocal of the big denominator. And then this is just multiplication. Let's start factoring those expressions that we can factor. For example, this 2x plus 4, 2 is a common factor. 3x minus 9, 3 is also a common factor. X squared minus 4, you can factor that. That's difference of two squares. So if we do that, 2x plus 4, it becomes 2 times x plus 2. 3x minus 9, it becomes 3 times x minus 3. X squared minus 4, it becomes x plus 2 times x minus 2. Now, normally, if you just have 6x or 6 or any number, you don't have to factor the number, the actual number. However, we are doing that in this case. The reason is because we will be able to cancel something. Particularly, you have 6 that's equal to 3 times 2, and there is a denominator 3 also. So 3 is a common factor. That's why we factored 6. If there's no common factor for the constants, for those numbers, you don't have to factor it. Okay? Anyway, so we can cancel x plus 2 here and x plus 2 here. And we can cancel 3 and 3 in here. So after canceling, we will have this guy here. Okay? And you see here, there's a 2 times 2. You can write the final answer this way. You can also write the final answer as 4x in the numerator. Okay? So this is also an acceptable final answer. Okay? 4x over x minus 2, x minus 3.
Sorry,
So,
sir.
yep,
Oh, so in the one there where it says the one above this line that you're on right now, how did you get that second three over there in that bracket? Not that three, the one next to it. Over there, sir, like the one next to that red three in that bracket.
this x minus 3, do you mean?
Yeah, yeah.
Yeah, because 3 is a common factor. Your 9,
Oh,
it's 3
yeah.
times 3.
Okay, thank you,
So
sir.
you can factor out the 3. Yes, you're welcome. Okay. Now, I just want to explain further the reason, the one I was explaining earlier, that you don't have to factor those numbers if there are no common factors. For example, say you have 9 over 10, and then you have something in here, whatever. Of course, your 9, that's factorable into 3 times 3, and then you have the expression. And then your 10, it can be factored into 2 times 5. And then there's some expression here. Even you factored this 9 and you factored this 10, there are no common factors between them. Okay? So you can just leave 9 over 10 instead of writing 3 times 3 over 2 times 5. Okay? And that is why in here, you have here 2 times 2x. The final answer 4x in the numerator is also acceptable. The reason why we just have here 2 times 2x, it's because the 2 was on the other expression, and the other 2 here is with this expression here. So that's the reason why they are originally separated. Okay? All right. Let's have this expression here. So we want to simplify x squared plus 7x plus 6 all over x squared plus x minus 6. Sorry, the all over thing. So x squared plus 7x plus 6 over x squared plus x minus 6 divided by x squared plus 5x minus 6 over x squared plus 5x plus 6. So as you can see, the line in here for my division symbol, it's longer than the other two lines there. So you will easily see what the big numerator and big denominator are. So from here, we, we apply the definition of division. We convert this to multiplication. So again, just keep an eye on this. For the numerator of the big denominator, you have x squared plus 5x minus 6. Okay? And then the denominator is x squared plus 5x plus 6. And look at this, they interchanged location. Okay, so I actually have the reciprocal. And then from here, you just simplify or you just factor each expressions here or each expression here. So you will have this factored form. X squared plus 7x plus 6, you can factor it into x plus 6, x plus 1. X squared plus x minus 6, you can factor it as x plus 3, x minus 2. This guy here, x squared plus 5x plus 6, it's x plus 3 times x plus 2. And then this guy here, x squared plus 5x minus 6, that's x plus 6, x minus 1. So again, factoring is really, really crucial. So I suggest that you use the weekend if you have time to practice on factoring. It's a very long weekend. Tomorrow is a holiday. And on, of course, Friday, I don't know if you have work or whatever, but at least you have extra day for a weekend, quote unquote. So we see x plus 6 here is a common factor. We also have x plus 3 here as a common factor. And yeah, after canceling them, we will end up with this. And notice, I am writing the final expressions or the final expression in factored form. Okay? So now we will look at addition and subtraction of rational expressions. Compared to multiplication and division, addition and subtraction of rational expressions is more difficult. Okay? So, um, well, you will realize that it's actually harder to add and subtract rational expressions than to multiply or divide them. Okay, so let us recall some things that we already know, at least when we try to add fractions or subtract fractions. So the first is if we have a over b plus c over d, okay, meaning you are adding fractions with the same denominator. So the denominator here it's b. All you need to do is to add the numerator. So you have here a plus c all over b. And of course, if you have a over b minus c over b, again, the same denominator, all you need to do is to subtract the numerators. So a minus c over b. And then what if you are adding or subtracting rational expressions, but you don't have the same denominator? So the most general way of doing that is this. So in here you have a over b plus c over d. Okay. Um, your denominator will become the product of the denominators. Okay. So you have your bd. And then for the numerator, what you do here is, I'll say, quote unquote, um, cross multiply the denominator to the other numerator. So in here you have AD, and then of course you retain the operations used. So AD plus BC. So A times D plus B times C. And if you have subtraction, of course, the same method, except that we are now subtracting. Okay? But this is what actually happened in here. Okay, so I'll show you this method. What really happened in here is that you look at the common denominator, possible common denominator. Okay, so you have here b for this expression here. Okay, and then you have here d for the expression in here. So you only have b in this expression. You want to have also d for this expression. So what you're going to do, or what you can do, is that, so originally you have a over b. What you do is you multiply d over d. You are multiplying 1, correct? If you have a number, non-zero number, you divide it with itself, you'll get 1. So d over d, this is just 1. And therefore, you are just multiplying a over d with 1. And you are not changing anything. Okay? And then similarly, you do that to the other expression, c over d. But this time, you already have the d here. You want to have a b. So what you do for c over d is to multiply b over b. And again, you are just multiplying 1. Okay? This is just multiplication of fractions. This is also just multiplication of fractions. So it can be simplified as AD over BD plus BC over BC. BD. And notice, BD now is the denominator for this expression. Also, BD is the denominator for this expression. So now, they have the same denominator. You can go back to this. Okay? They have common denominator. So all you need to do is to add the numerators. That's why you have here AD plus BC. Okay? And of course, for subtraction, the same method. Okay? Is that clear? Addition and subtraction of rational expressions. Now, for these two guys here, there is a possibility that the final expression is still simplifiable. Meaning, the final expression here, okay, can still be simplified. So you have to make sure that you rewrite this expression here and simplify them. Similarly for this, there's a possibility that you can simplify this expression. So just try to factor the expressions that you will see in the rational expression and then cancel the common factors. Okay? So, for example, let's have this. Perform the indicated operations and simplify. Leave the final answer in factored form. You have 3x squared over 2x minus 1 minus 9 over 2x minus 1. So the denominator, they are the same, 2x minus 1. And because they have the same denominator, all you need to do is to combine the numerator and then copy the denominator. So this will be 3x squared minus 9 all over 2x minus 1. So 2x minus 1. The denominator is just 2x minus 1. And for this, 3 is a common factor. So you can just factor that out. And you have your 3 times x squared minus 3 all over 2x minus 1. If you look at x squared minus 3, this is not factorable anymore. Of course, 2x minus 1, it's prime. You cannot factor that also. And this will be your final expression. Okay? Next, let's look at our next example here. You have 2x minus 3 over x minus 1 minus 2x plus 1 over x plus 1. So for this example, we don't have the same denominator. So we use the other method or this guy here. This guy here. Particularly this because we have subtraction there. Okay? So in here, you have the following. So for the denominator of this difference, you just multiply x minus 1 and x plus 1. And then for the numerator, you need to do cross multiplication. Okay? So we do that. Denominator, it's x minus 1, x plus 1. For the numerators, you do the cross multiplication. You have 2x minus 3 times x plus 1. That's in here. Then we have the minus here. And then 2x plus 1, that's this guy. And then x minus 1, that's the denominator of the other expression. And then from here, The numerator, you need to simplify this. Okay? This is not in factored form because you still have an outer subtraction in here. Okay? The denominator, well, it's already in factored form. So just retain that x minus 1, x plus 1 in the denominator. So we simplify all of this. 2x minus 3 times x plus 1. You multiply that. You will have 2x squared minus x minus 3. And then there's a minus here. Take note of that. That's still minus here. Then you multiply these two guys. We have 2x squared minus x minus 1. And then from here, we distribute this negative. Take note of that. I'll just write it here. So for this guy here, this is equal to negative 2x squared. Then we have plus x, and then we have plus 1 after you distributed this minus over this grouping. And therefore, you have here 2x squared minus 2x squared. They'll just cancel. Minus x and then plus x. They'll also cancel. And then you have minus 3 plus 1. That's your negative 2. And then the denominator, it's still x minus 1, x plus 1. Okay? So you can write the final answer this way. Okay? Or you can bring this negative outside of the rational expression. So you can write the final answer this way, or you can write it this way. Negative of this expression. So they mean the same thing. Okay? Questions? Let's do another example here. We have x over x squared minus 4 plus 1 over x. So denominator here, it's x squared minus 4. In here, the denominator is x. So they don't have the same denominators. So we do again the more general addition or subtraction of rational expressions. So from here, the denominator of the sum, you just multiply the denominators here. And then for the numerator, you cross multiply so that we will have this. We have, for the denominator, we have x times x squared minus 4. For the numerator, we have x times x here. It's coming from this times this guy. And then we have x squared minus 4 here. It's coming from 1 times x squared minus 4. And then we just simplify this, x squared. This guy here, x times x, it's x squared. So you have x squared plus x squared in here. And you have 2 x squared minus 4. And then since we want our final answer to be in factored form, we factor x squared minus 4 because that's still factorable. You have x minus 2, x plus 2. And in here, we can factor out 2. Because there's a 2 here and there's a 4 here. 2 is factorable. So we will end up with this final expression. Okay? Now, listen. There are some students who do this. Okay? You have your x over x squared minus 4 plus 1 over x. Some students do this. oh, there is an x in here and there is an x in here, I can cancel them. So that we will end up with what? 1 over x squared minus 4, well, plus 1. This is not correct. You cannot cancel them because they are from different expression. You are adding, okay? You are adding. If this were multiplication, yes, you can cancel them. But this is addition. You cannot do that, okay? Another thing, some students do this. You have x squared over x squared minus 4, okay? Oh, I can see the x squared here and the x squared here. I'll just cancel this and this. And then they will end up with what? 1 over 1 minus 4. This is equal to 1/3. Again, this is not correct. Okay? So don't do that. You cannot cancel this guy here with this guy here because this is subtraction in the denominator. If this were multiplication, x squared times 4, yes, you can cancel that. Okay? But on this form, you cannot do that. So do not ever try doing this in my course because they are not valid and they are totally wrong. Okay? Questions? Now, there is like I said earlier, there is a possibility that when you do the addition or subtraction of rational expressions, there's a possibility that you can still simplify them or you can still simplify the sum or the difference. In this case, we didn't see that. But for other cases, you will see cancellations. That's why you were asked to write everything in factored form because of that possibility. Okay? So there is another method in adding or subtracting rational expressions to at least avoid that cases. Meaning um, you avoid forgetting cancellation of common factors. So we call this method the LCD method. We start with the least common multiple. So given two polynomials, p of x and q of x, the least common multiple is a polynomial of least degree that has each polynomial as a factor. Okay? So the to find the LCM of two polynomials, what you do is to factor each polynomial. That's your first step. Your second step is you find you look at the factors of each polynomial, okay? And then you multiply these factors, okay? And then the degree of each factor that you are multiplying must be the highest power that you see as a factor of a polynomial. Okay? So the LCM is the product of each of these factors raised to a power equal to the greatest number of times that the factor occurs in all of the polynomials. To see this clearly, suppose you have this p of x equals x squared minus 1. That's x plus 1 times x minus 1 when you factor it. Q of x, if you have x squared plus 2x plus 1, when you factor it, it's x plus 1 squared. So you see, P of x has factor x plus 1. It has factor x minus 1. Your Q of x, it has factor x plus 1, and it is being raised to power 2. All in all, the factors that you see are x plus 1 and x minus 1. This is also x plus 1. Okay? So according to this step 2, okay, the first few phrase here, the LCM must be a product of these factors. So it will be a product of x plus 1 and x minus 1. Okay? The other part of the statement is the factors are raised equal to the greatest number of times the factor occurs. In this polynomial P of x plus 1 has power 1, x minus 1 has power 1. In the polynomial Q of x plus 1 has power 2. So, the LCM will be this. You have the product of x plus 1 and x minus 1. The powers are the highest power that we see. This has power 1, this has power 2, the higher number is 2, so you have that power 2 here. X minus 1 has power 1 in here. There's no x minus 1 in here. That's why the x minus 1 here has power 1. So this is the LCM. Okay? Another one here. Suppose you have these polynomials in factored form. You have x times x plus 2 squared times x minus 2 for the polynomial P of x. For Q of x, you have 2 times x plus 2 times x minus 2 to the 4. So what is the LCM? The factors that we see here are for P of x, that's just x, x plus 2, and then x minus 2. For the Q of x, you have 2, x plus 2 also, and x minus 2 also. Okay? So if we look at the LCM of this, it should be a product of all the factors that we see. I have the factor x, I have the factor x plus 2, I also have the factor x minus 2 here. In here, I have the factor 2. I have the factor x plus 2, but I already wrote it. I have the factor x minus 2. It's already here. Okay? But what are the powers of these factors? The power of x here, it's 1. This has no factor x. So the power of x here, it's 1. So I'll just have x to the 1. The power of x plus 2 here, it's 2. The power of x plus 2 here, it's just 1. So the higher number, it's 2. So I'll put power 2 for the LCM. The power of x minus 2 here, it's 1. The power of x minus 2 here, it's 4. The higher power, it's 4. So I'll put power 4 in the LCM. And then here you have the constant 2. The power of the 2 here, it's 1. In the P of x, there's no 2 there. So the power of 2 here, it's just 1. So this is the LCM for the polynomials P and Q. So that's what you will see in here. Okay? So This is LCM. When we add or subtract um, rational expressions using the LCD method, okay, we look for the LCM of the denominators. That's why it's called LCD. LCM, least common multiple. LCD, it's the least common denominator. Okay? So, rational expressions can be added and subtracted using LCM method or LCD method. This is helpful when the denominators of the rational expressions have common factors. Okay? So, if you are adding or subtracting two rational expressions, you start with factoring the denominator to see the LCM or the LCD. Okay? So, the LCM method for adding or subtracting rational expressions, or the LCD method, okay? You find the LCM of the denominators, called the LCD. Write each expression using the LCM as a common denominator. So, this will be explained later in the example, but I have shown you this. I have shown you this when we try to add A over B plus um, C over D. Okay? We actually did uh, almost similar to the LCM method. When we multiply this by D over D, and in here when we multiply this B over B. Although we are not sure if BD it's the LCM of the denominators, but that's how you're going to do it. You multiply and divide the rational expressions with something that is missing, okay, that is missing in the original expression but should have been at denominator to complete the least common multiple. Okay, so I'll explain that further later. And then since you have same denominators after doing step 2, you can add and subtract the usual way, meaning adding and subtracting expressions with common with the same denominator. Okay, so let us look at this example. Okay, so you have these expressions: x plus 4 over x squared minus x minus 2 minus 2x plus 3 over x squared plus 2x minus 8. So like I said, you start with factoring of denominators. Denominator here, x squared minus x minus 2. You will have x plus 1, x minus 1. And then for this, you have x plus 4, x minus 2. That's the factored form of x squared plus 2x minus 8. So as you can see, if you have, say, if you have your p of x, if you have your p of x to be x squared minus x minus 2, which you were able to factor into x plus 1, x minus 2. Your q of x, it's the polynomial x squared minus 2x, sorry, x squared plus 2x minus 8. And you're able to factor that into x plus 4 times x minus 2. The LCM will be the product of all the factors that we see. We have here x plus 1 from here. And then we also have x minus 2 from here. And then from here, we have x minus or x plus 4. And then in here, we have x minus 2, but we have written that. Okay. So that's the first step in, or at least the second uh, step, first part of finding the LCM. The second part of the second step is to find the highest power. But anyway, the power of x plus 1 here, it's just 1. Here, x minus 2 has power 1. Here, x plus 4 has power 1. Here, x minus 2 has power 1 also. So all of these factors have power 1 only. Okay? So this will be the denominator. Okay? This will be the denominator of these two expressions here. So how are we going to do now? What's our next step here now? So originally, you have x plus 4 over x plus 1 times x minus 2. But the LCM, it's x plus 1 times x minus 2 times x plus 4. Okay? And I don't have x plus 4 in the denominator here. And I have to have that. I need to have that. So I'm going to multiply and divide by x plus 4. So I'll also put the x plus 4 here so that I am not changing the actual or the original expression. Okay?
Um,
Yes.
about the LCM, when px and qx have the same power for each denominator, we have to put them all on the LCM.
Yes, you have to use the highest power. So if they are the same, then that's what you're going to put.
Okay.
Yeah. So for this, we have for this expression, we have this. And then for the other expression, you have 2x plus 3 divided by x plus 4 times x minus 2. LCM, it's x plus 1, x minus 2, x plus 4. So looking at this, I don't have the x plus 1. So I'll multiply and divide this expression by x plus 1. Okay? And now, this expression here and this expression here have have the same denominators. X plus 1, x minus 2, x plus 4. That's the same as this one. And of course, don't forget to multiply the numerators now for this and also for this. Okay? So you will see that here. So in here, you have x plus 4 and x plus 4. You have to include that now to have a common denominator. In here, you have x plus 1 and x plus 1. And since they have common denominator, you can now combine them using the first way that we had. You have a over b plus or minus c over b. So this is a plus or minus b over plus c here. Okay? So this is now the one we're going to use. Of course, you have to expand this and then simplify everything. So for this guy, this is x plus 4 quantity squared. You will end up with this, x squared plus 8x plus 16. Then there's a minus here, so you have a minus here. And then you have this, 2x plus 3 times x plus 1. If you multiply them, you will have this guy here. And then you just need to simplify. So again, For this guy here, this is what? Minus 2x squared minus 5x minus 3. Okay? So if you simplify that, you have here x squared minus 2x squared, then 8x minus 5x, and then 16 minus 3. So if you do that, you will end up with this expression. Minus minus x squared plus 3x plus 13. So that's your numerator. And of course, the denominator, you just copy this. Now, you need to check if this numerator here, it's still factorable. But you will see it's no longer factorable. You can do that. Your A, that's -1. Your B, that's 3. Your C, that's 13. So B squared minus 4AC. So you have 3 squared minus 4 times -1 times 13. So this is equal to 9 plus 52. This is not equal to 0. So this numerator here, it's not factorable anymore. So this is our final expression. Okay? Questions? Okay. Next, let's have this x over x minus 1 squared plus 2 over x minus x plus 1 over x cubed minus x squared. So you are now adding 3 expressions here, 3 rational expressions here. So again, you look at the LCM. So we have this. Our P of x, that's x minus 1 squared. Our Q of x, that's just x. Our, let's say, R of x, it's x cubed times, or x cubed minus x squared. But if you factor this, you will get x squared times x minus 1. So for the LCM, the factors that we see are, we have x minus 1 in here. So let's write that x minus 1. Okay. X minus 1. We have x in here. So we have x. And then in here you have x and x minus 1. They are already written. Now, what is the power for these factors? In here, you have x minus 1 power 2. In here, there's no x minus 1. In here, we have x minus 1, but it has power 1. So the higher power, it's 2. So we put this as 2. Next, here we have x power 1. This guy here does not have factor x. In here, we have x with power 2. So the highest power that we see is 2. So we put x squared in here. And this will be our LCM. Okay? So we need all denominators here to be x squared times x minus 1 squared. So we adjust each expression here. Okay. So for the first, so I have factored it in here. For the first expression, recall again your LCM, it should be x squared, x minus 1 squared. For the first expression, we only have x minus 1 squared. So I have to multiply x squared on the denominator. I have to do the same thing in the numerator. That's why you see this x squared here and x squared here. For this expression, originally I only have x, but I need x squared. And also I need x minus 1 squared. So to complete this, from x, I have to multiply x times x minus 1 squared. Okay? And of course, in the numerator, I'll do the same. For this expression, I have x squared times x minus 1. So I have x squared, that's fine. But I need x minus 1 squared. So I have x squared, x minus 1. I need x minus 1 squared here. So I have to multiply x minus 1 in the denominator. And I'll also do that in the numerator. Okay? And then from here, you just multiply um, this guy here, and this guy here. You combine all of them and then simplify. So for x times x squared, that's x cubed. Here we have 2x. That's why you have 2x. This is plus. So this is plus here. We have x minus 1 quantity squared. So you multiply that and you'll get x squared minus 2x plus 1. Then here we have the minus. That's why we have a minus in here. And then we have x plus 1 times x minus 1. We have here quantity x squared minus 1. So we still need to multiply this 2x inside this. And we have to distribute this minus. Okay? So if we multiply this inside this, you have 2x times x squared, you have 2x cubed. 2x times negative 2x, that's minus 4x squared. Then 2x times 1, that's 2x in here. While in here, you have to distribute the minus. So negative x squared, that's in here. And then negative times negative 1, that's positive 1 in here. Then finally, you just need to combine like terms. It's just this guy here and this guy here. So you will have this expression. And then as of this point, I'll just say that this is no longer factorable. Okay? So this is the final expression. Questions on the LCM method? Okay. Now we know how to work on the rational expressions. Okay. We know how to add and subtract them. We know how to multiply and divide. Okay. And we know a method, another method for adding and subtracting them called the LCM method. So Let's just discuss complex rational expressions. So complex rational expressions, this is just a rational expression where the numerator of that rational expression or the denominator of that rational expression is another rational expression, or maybe a more complicated expression. That's why complex rational expression. So if the numerator or denominator of a quotient involves rational expressions as well, then the quotient is called a complex rational expression. So for example, here, you have 2 plus x over x plus 1 all over 1 minus x plus 2 over x plus 1. Similarly for this, you have x squared over x squared minus 1 plus x all over 3 minus 4 over x minus 1. So these are complex rational expressions. When you have this, of course, our goal is to simplify it. Okay? Our goal is to simplify it. When simplifying a complex rational expression, we may use the following two ways, or the following ways, or even a combination actually. Option 1, we treat the numerator and denominator of the complex rational expression separately. So you work on the big denominator first, you work on the big numerator first, you simplify each. And then it's like if you, what you're going to do is to make a single rational expression for each numerator or denominator. And then it's like a quotient. It will become of um, a quotient of rational expressions. And we know how to divide rational expressions. Okay? And once you have that, you simplify. Another option is with the use of LCM. So you look at the denominators of the big numerator and big denominator. You look at, you find the LCD, least common denominator. That is to say, you need to find the LCM of the denominators that you see in the big numerator and on the big denominator. Once you have the LCM, you're going to multiply both the big numerator and big denominator by the LCM. And then you simplify. Okay? To illustrate, let's have this. We want to simplify 2 plus x over x plus 1 all over 1 minus x plus 2 over x plus 1. So we start with this expression. Okay? And then in here, we look at the numerator and work on that. We combine that, we add this expression here, and we will get this guy here. It's just addition of two rational expressions. Take note, if you have a number, say r, this is also the same as r over 1. So it has a denominator. The denominator is 1. So you can rewrite this 2 here with denominator x plus 1. Okay? This can be written as 2 times x plus 1 over x plus 1. Okay? And therefore, this expression here, you will get this. That's for the big numerator. You do the same thing for the big denominator. Okay? 1 minus x plus 2 over x plus 1. So you have here x plus 1 minus quantity x minus 2. So don't forget the grouping. Okay? And then from here, you just need to simplify everything and then use the definition of division. So from division, we convert it to multiplication, but don't forget to get the reciprocal of the big denominator. So in here, you have 2 times x plus 2 times 1. That's why you have 2x plus 2 in here, and then plus x. Then, of course, over x plus 1 in here. Then the reciprocal of this, the denominator x plus 1 becomes numerator. For this, we distributed the negative. So I still have this x plus 1 in here, but distributing this negative, we will have minus x and then minus 2. So you simplify everything. Notice x plus 1 here, x plus 1 here, common factor of numerator and denominator. They will cancel each other. For this guy here, if you simplify, you have x minus x, so that's just 0. And then here 1 minus 2, that's your negative 1 in here. For the numerator, here you have 2x plus 2 plus x, you have 3x plus 2. And then x plus 1 is a common factor. You can cancel them and you will end up with this expression. Yes.
Sir, is it only when we are reciprocating like the numerator that we change the signs?
There is no change in sign.
Yeah, like when you did like in the first one it was x plus 2 and then it becomes x minus 2.
Because this one here, it's minus.
Okay.
So this is 1 minus this whole thing. So you have to put that minus.
Okay. Got it.
So it's like you have your 1 minus x plus 2 over x plus 1. But your 1, you can write it as x plus 1 over x plus 1. That's still 1, correct? Then minus x plus 2 over x plus 1. So if you combine this is the numerator minus this numerator here because they have the same denominator. So you minus this whole thing. And that's why you have x plus 1 minus the whole thing, x minus 2, divided by x plus 1. That's why we have that minus.
Thank you.
You're welcome. So you can write the final answer this way, or you can distribute the negative. You can write it as minus 3x minus 2. So it's totally fine. Okay? So what we did here is the first option. We treated numerator or the big numerator and the big denominator separately. And then you have um, the expression, and then you simplify. Another example here, you have x squared over x squared minus 1 plus x all over 3 minus 4 over x minus 1. Okay? So from here, we look at this x, we look at the expression, and then we treat them separately. So for the big numerator, you can rewrite it as this way. So again, you only have x in here, but that x that's equal to x over 1. So it has a denominator. Or maybe you can write your x as x times x squared minus 1 divided by x squared minus 1. So it will have common denominator with this guy. So if you do that, you will have this expression for the big numerator. You do the same thing for the big denominator. Your 3, you want the denominator x minus 1, so you write 3 as 3 times x minus 1 over x minus 1. So you can combine it with this 4 over x minus 1, and you will get this. And then from this division, we turn it to multiplication. Look at this. From 3 times x minus 1 minus 4 over x minus 1, when we convert it to multiplication, we get the reciprocal, which is x minus 1 over this guy here. This guy here was obtained by, well, distributing this 3 over the sum. So you have 3 times x, that's your 3x here, and then 3 times negative 1, that's minus 3 here. And there's still your minus 4. So you just distributed it. Furthermore, in the big numerator, you distribute this x so that you will have x cubed minus x. So x times x squared, that's x cubed. X times minus 1, that's minus x. And then the denominator, here you have x squared minus 1. And you have factored it into x minus 1, x plus 1. And as you can see, you can cancel the x minus 1 later. For this, you have x squared plus x cubed minus x. You can factor out x. Okay? And then here you have minus 3 minus 4, you'll get minus 7. So for this, you factored out x because x is a common factor for this expression. So x times x squared plus x, x times x plus x squared minus 1. That's for this guy. And then for the denominator here, it became 3x minus 7. And then x minus 1 here is cancelled because it's a common factor. And there are no other common factors, so you can write now the final expression this way. Okay? So x times x squared plus x minus 1 all over x plus 1 times 3x minus 7. Okay? Questions here? Okay. So in both examples, what I did was to use option 1. So what I'm going to do next is to use option 2, the LCM method. Okay? But I will not put that on record. So try to work. If you want to do this, the LCM method, the option 2 method, you do that. Okay? And for those who are still here, you will see how I'm going to do it. Okay? But if you are rewatching this, you will not be able to see how I'm going to do the LCM method. Okay? So that's it for today's lecture. Again, I ask you, or I suggest that you do some problems from pages 28 to 30 of the 016 module so that you'll have a lot of practice.